Our next speaker today is Bart Schols. Bart is in technical sales support for Desmet Ballestra. He's coming to us from Belgium today. He has a master's degree in agrochemical engineering. He worked in the edible oils industry for 5 years in refining plants as a project manager, and then worked on process optimization in a fractionation specialty plant. He joined Desmet Ballestra in 1998 as a process engineer, and after some years of product management, he was the engineering manager for the refining and modification department. And he just recently moved into the group sales support. His presentation on soybean oil refining is something I think you'll find very interesting. Bart, welcome today, and thank you very much for your talk.
Okay. Good afternoon, everybody. So my name is Bart Schols. Mark, thanks for the nice introduction. And I'd like to thank also the previous speaker, Matt, for the very nice general framework of tendencies in the refinery. In my presentation, I have decided to zoom in on the first steps of the oil refining. That means where we have the separators, so where we have neutralizing or degumming. So it would go like this. I would give an introduction where I will explain shortly the difference between chemical and physical refining. Then we will zoom in a bit on chemical refining, and I will introduce nano cavitation technology. And then as alternative, I will zoom in on physical refining and also what is actually happening in degumming processes today with the very fast evolution of enzyme technology. And then, to be complete, we will also shortly discuss water degumming and the potential use of enzymes in water degumming with, as alternative, a gums deoiling process. So, the tendencies in refining are actually, everybody who is producing oil will always be between different requirements. Of course, the oil quality is one criterion that you have to respect. And then the other criterion is the refining cost. And that all in a framework of more and more evolution towards sustainability. So less environmental issues, less energy consumption, and so on. So basically, on the one hand, in an existing plant, you can play with the refining conditions. But on the other hand, for a new plant, of course, all depends on the plant configuration. That will actually define how you can, which process you can run. So the quality is one thing. The cost has to be minimized. There are all kinds of legal requirements as environmental. And then, of course, the sustainability is something that comes more and more in the picture. So we have to look for processes which consume less chemicals, less energy, give less effluent, which are safer. And as also already said, there is a tendency towards more mild operating conditions. To have less negative side reactions. But when for this presentation, I'd like to simplify a bit the issue. So, of course, things are more complex than that, but to explain the difference between chemical and physical refining, I think we have to zoom in on the two major components which we have to remove from a crude oil. So, of course, there are the free fatty acids, which have to be removed, and the phospholipids, which have to be removed from the oil. The FFA can be removed basically as soaps after the addition of caustic soda. And that is what we call chemical refining. And as an alternative, the free fatty acids could also be removed from the oil by distillation in the deodorizer. Now, soaps and phospholipids are emulsifiers. So unfortunately, when you try to remove that from an oil, unavoidable there will be losses going together with it, simply by the fact that these molecules are emulsifiers. And the soap stock or the gums is a water phase, so you get there an extra loss. On this slide, you see on the top, you see the crush, the preparation and the extraction. And then you have the water degumming. And then you have on the left side, the chemical refining, and on the right side, the physical refining. It looks more or less similar, but as said, the difference is that the fatty acids will be removed with the soap stock in a chemical refining line, and in the deodorizer with the distillate in a physical refining line. So the exact point of when chemical or physical is the best thing to choose depends, of course, on many factors. One of the factors is the FFA content of the oil, but another factor is the cost of the oil. The lower the cost of the oil, maybe the more in favor of chemical refining, but the higher the value of the oil, the more in favor of physical refining. Also, what is more and more, the effluents are a real concern. And for that reason, there is also a tendency to go to physical refining. Actually, for the people who are in R&D or who are not in production, it has been a dream for decades to move for all oils to physical refining. But the reason that that is not yet done is because it's not always so easy. So I would give this comparison between chemical and physical, let's say, before we introduce the new technologies. I would summarize chemical refining as follows. It is applicable for all oils. It is not too complicated process. It allows for mild deodorizing conditions. That is all positive, but let's say the side effect is that you produce soap stock, that you need a soap stock splitting, unless you have an integrated plant where you can dose the soap stock on the meal. And then you have their effluent with phosphates and sulfates, which is sometimes a headache depending on the local environmental legislation. The distillate that you will produce in the deodorizer will have low FFA, but higher unsub content. So I would say it has been, and in most plants for soya, it is installed like that. It is a reliable process for standalone refineries, and the process can deal with virtually any oil quality. Now, when we look to a physical refining, that is, of course, a must for tropical oils. And it is a process that goes fairly well for easy, fresh, soft oils. It is a process which can be difficult for old, low-quality soft oils, which are traded or stored for a long time. Also, if people want to go for physical refining, the deodorizer has to really work as per design with the correct vacuum to be able to strip the fatty acids from the oil. This process gives less effluent, no soap stock splitting, and gives a higher FFA distillate. So I would say this is a good option for integrated plants, and it is, for instance, for soya and corn oil, obvious to go for physical refining. For soybean oil, there is sometimes resistance because the quality is not always allowing for this process. So when we look at the neutralization line, to get it right, the main thing is to do the dosing of chemicals correct. So that has all has to be automated. The exact quantity of chemical that you dose has to be correct. But it's more complex than that. You also have to use the right concentrations. So for instance, not only the quantity of caustic is important, also the exact concentration that you work with. That is then again dependent from the FFA. And also the right access is important to get a good separation on the separator. Of course, there are many electromechanical issues which have to be properly selected to get a good result, like the disc stack, the exact pressure on the hydrohermetic feed of the separator, the back pressure, and so on. So I would say it is a reliable process, but it gives soap stock, and you have the effluent. So now the question is, how can we further improve chemical refining? We already said that the soaps and phospholipids are emulsifying components, and so they give oil loss. Now, if we can tackle this oil loss one way or another, we are a step ahead. So which technology could help us for that? When we look at the history, the last 50 years, you see that actually for chemical refining, 50 years ago, people were dosing acid in the storage tank. And then after that, people invented to start dosing in line, in the neutralizing line. And we see also that mixers have evolved from static mixers to dynamic mixers to high shear mixers. And so the question is, can we even go further in this mixing of chemicals in the oil? Well, we have introduced hydrodynamic cavitation technology in the chemical refining process. So basically, it is a static mixer, to simplify it, but with some special geometry, with some internals with a special geometry, which allow to have a controlled cavitation. I know that when you hear cavitation, most of you will think about negative things of cavitation. Cavitation can destroy a pump. It is something you don't want in a centrifugal pump. But here the cavitation is used to increase the shear rate and to actually to take benefit of it. And it's also a controlled cavitation, so to assure that there is no damage of the nano reactor. We work for that together with the company CTI, and a nano reactor is not very big. What we have observed is that with this technology we can drastically reduce the chemicals. We can also minimize the excess, and due to that there is a direct impact on the yield of the line or the oil losses, which are reduced. Here is a picture of how it looks like. So the advantage is it's not taking a lot of space. You see this rectangular box in the middle of the screen. In that box, there are these nano reactors. And it is a kind of static mixer, but it works with a pressure difference of 60-70 bar. So a very high pressure difference. And to overcome that, we are using a multicellular pump, which you see on the right side against the wall. That is actually the most reliable pump to go for this, to feed this nano reactor. What we also see on the result is that we have a lower soap content. And so you could work with less wash water to get the soaps down after the second separator. And there are even some customers who are skipping the washing step. So to summarize the advantages of nanotechnology in neutralizing, we can drastically reduce the need of phosphoric acid. And with that, the caustic soda goes down. And also the need of excess is actually eliminated. And on the quality, we see that we get a lower soap content, and lower phosphorus in the neutralized oil. We see also a reduced oil loss. This is actually how it looks like, these reactors, and according to the capacity, they will be built in a skid. And we have, for instance, on the right side, you see 3 nanoreactors in parallel to reach a certain capacity. At the bottom, you see again the multi-stage centrifugal pump, which is a more economical alternative to the piston pump on the right side, which is rather expensive. Here, this slide, you see some results that we had with and without nanotechnology on the use of chemicals and also on the result after neutralizing. So this is, I think, really something new in neutralization technology. And it is also something what is in line with the tendency to go for a more sustainable process. So using less chemicals, less water, and this is also allowing to increase the yield and to lower the operating cost. Then the second part of the presentation is on physical refining. Actually, when we look at degumming the last 30 years, and we look at the history of the processes that were introduced in the industry by all kinds of suppliers or even by refiners themselves, actually one could ask a question. If the first was invented, why people were still looking for a next degumming process? The reason is very simple. Because an oil can be easy or difficult, and it's not like that every process could simply reach the results that were expected from it. So people were continuously looking for improvements on the degumming process. And when you look at the history, you see that actually, just like in neutralization, the dosing itself is very important. The automated correct dosing of chemicals, then the ice-shear mixers are extremely important to get a good result. We also see that the dilution of acid is, especially in degumming, is very important to get good results. The pH correction has to be done to be able to remove the phospholipids correctly. Then we have things like 2 steps degumming with recycling of the heavy phase. And even some people go for 3 steps in degumming. And also there can be a maturation step at reduced temperature. These processes are still used today in the industry. And for some oils, they are fairly reliable as there are sunflower oil or corn oil. For soybean oil, it's less common to use this process because it's not always easy. It depends a lot on the non-hydratable phospholipid content. And we should not forget that at the end, the target is to get the phosphorus low enough. If not, we will be penalized in the bleaching downstream. So when we now look at the chemistry of phospholipids, basically we have 4 types of phospholipids. So a phospholipid looks like a triglyceride. You have 2 fatty acids on a glycerine molecule, and then you have a polar phosphate group on the 3rd connection point of the glycerine. And depending on what you have here, this X, you have actually 4 types of phospholipids. And 2 of them are fairly hydratable, and the 2 others are less hydratable. So if we could find a way to destroy these phospholipids, which are emulsifiers, we could reduce the neutral oil loss. Since a long time in biochemical textbooks, these enzymes were described. People who study microbiology or biochemistry, they are well aware of that. I think the big difference with 50 years ago and today is that these enzymes are becoming more and more commercially available. When Lurgi introduced the first enzyme degumming in Germany, that was still with enzymes which were extracted from animals, and that was not a real big success. But I would say from the moment companies like Novozymes or Desmet started to introduce enzymes, actually the whole thing is going faster and faster, and there are becoming more and more enzymes available, and also cocktails are becoming available. So if we think out of the box on this scheme, where could we actually think about using enzymes? Well, you could even think to use it in the extraction, but we could use it everywhere where phospholipids are a problem. For instance, in the water degumming, we could use it, or we could use it in a chemical refining, or we could use it in the deep degumming, or we could use it to process the gums downstream. It's also important to make a difference between deep degumming and water degumming. So the purpose of deep degumming is to really remove the phosphorus below 10 ppm. If we do a water degumming, normally we have to reach a phosphorus spec of like less than 200 ppm for soybean oil. And in a typical water degumming, you could achieve that unless the beans are of lower quality and contain a lot of non-hydratable phospholipids. But if we look at the different enzymes, we see here on this slide where actually these enzymes are working. So an enzyme is a protein with catalytic activity, which is produced in microorganisms. And these enzymes are basically cutting the molecule. For instance, PLA1 is cutting off a fatty acid from the phospholipid molecule. And a PLA1 is a phospholipase which cuts off the middle position. And a PLC enzyme is actually cutting off the complete phosphor group. Then you see, as a result, with the PLA, you get a lysophospholipid, but with the PLC enzyme, you even get only diglyceride as a result, plus a water-soluble phosphor group. Diglycerides are actually neutral oil. So here we have a typical degumming line, and we have shown how this could be modified for enzyme degumming, deep enzyme degumming. The acid conditioning upstream remains very important to make the phospholipid accessible for the enzyme. And we also have to correct the pH for the enzyme. We have to cool the oil, and we have then to dose the enzyme in the oil. And in this reactor, the enzyme will do its work and try to destroy the phospholipids as good as possible. So typically we work with 2-3% water, and the temperature will be 50-60 degrees for let's say for Licitase Ultra. There are today other enzymes which allow for a higher temperature, but I would not go into that detail today. Of course, the reaction time is also something that can be discussed, because the longer the time, the less enzyme we will need to get the expected result. So deep or complete enzyme degumming can be applied both on water degummed oils or on crude oils. It is still today always done with PLA1 enzymes. With the PLC type of enzyme, until today, it is not possible to go for deep degumming. Usually the phosphorus remaining in the oil will be like 50 ppm. Also, economically, at the end, the enzyme degumming is yield driven, because the enzyme has a cost, and so the purpose is to have less neutral oil loss. So in other words, the lower the phosphorus content in an oil, the less attractive to go for enzyme degumming. Apart from less oil loss, there is also more distillate, because when you cut off a free fatty acid molecule, you increase the FFA of the oil in degumming, and that will be removed in the deodorizer with the distillates. But as a conclusion, I would still say that the enzymes will be one factor to move more from chemical to physical refining. But we should not forget that at the end, we really have to aim at phosphor less than 10 ppm. Because if you go with 20 ppm to the bleaching, you will be penalized another way. I would also like to highlight that the acid conditioning remains very important also when we do enzyme degumming. So the enzyme can, of course, be applied for different oils and also in the pre-treatment of a biodiesel plant. So this is again summarizing what I already said. We have to reach low phosphorus, and the yield improvement depends on the initial phosphorus content. And the free fatty acids will be valorized in the distillate. So now, to be complete, I also would like to shortly talk about the water degumming bit, because all the traded oils are first water degummed normally. If not, it will be a big headache to ship crude oil containing 800 or 1200 ppm phosphorus. So in most crushes, there is a water degumming installed. And there also is a potential to use enzymes. The advantage is that you do not have to reach deep degumming, and we can thus apply different different enzyme, PLC enzyme. So in an enzyme-assisted water degumming, the phospholipids will be converted into diglycerides. The only thing is, where PLA1 and A2 for the deep degumming can destroy any of the four phospholipids, the PLC enzyme unfortunately is not cannot destroy all the four phospholipids, and that is also the reason why it cannot reach yet deep degumming. So usually the phosphorus will be around 50 ppm at the outlet of an enzyme-assisted water degumming. But, and especially for soybean oil, if we have there 2.5% phospholipids, the potential of yield increase is huge, of course. Because a phospholipase C is simply cutting off the phosphorus head, and what remains in the oil is the diglyceride. And diglyceride, we can say that it is neutral oil, actually. Here is a calculation which goes back to the molecular weights and the stoichiometric chemical reaction, but it's calculating basically the increase of diglyceride based on a phosphorus content of 845 ppm. Here also is we give actually the difference in FFA and diglyceride for an enzyme assisted water degummed oil compared to the crude oil. So you see diglycerides are increasing and FFA is also increasing, because today the PLC enzymes are commercialized as a mix also with PLA1 enzymes. Unfortunately, as said, it is not possible yet to do deep degumming today in the water degumming when using PLC enzymes. But the potential of yield increase is actually very high with this process. I think it's more and more applied in the water degumming, at least if the lecithin is not having a higher value. Because another tendency is for like organic soybean oil or non-GMO soybean oil, is that lecithin could have a higher value than neutral oil, and in that case, of course, the enzyme degumming cannot be used. Economically, we also have to look at the difference in value between oil and meal. So the bigger the difference, the more money can be spent for the enzyme. The lower the difference, of course, the less money that can be spent for the enzyme. So as a conclusion, enzyme-assisted water degumming on crude oils, usually with PLC or PLC-PLA cocktails, and applicable if the lecithin is not attractive. Higher oil yield is the main driver, and deep degumming is not possible yet. The economics is a pure economical calculation. Just to be complete, we have also developed a process where the enzyme is not dosed in the oil in the degumming line, but where the gums are processed on the site. So after separating the gums from the oil in the separator, we have a process where we treat the gums itself with the enzyme. This has several advantages. One of them is that we need much less enzyme. The second advantage is that the oil that you recover, you do not have to add it to the oil. You can also sell it a different way, because this is an oil containing a lot of diglycerides. And diglycerides is something what you do not always want to add to the oil. So you have the possibility to sell this oil separately. So the advantage of gums de-oiling is that you can process the gums offline, and that you also, the additional yield that you collect it separately, and you can give it different destinations. The flexibility is of course the same as for a normal degumming. You can always switch the use of enzymes on and off according to the meal price or the lecithin price. So as conclusions, and I'd like to start on the right side, PLC degumming and water degumming has a huge yield increase potential, and there is as alternative the gums de-oiling process with the same enzyme, but this can never reach deep degumming. If we want to do deep degumming to go for physical refining, we could indeed introduce enzymes to get even better result. But as always, the oil quality will be a limiting factor. So with the use of enzymes, we can further reduce the loss. Also, when using the enzyme for deep degumming, the acid conditioning remains a key factor. And for the physical refining, I would say somehow the oil quality at the inlet is still one of the factors not to be overlooked. So when we go to the chemical refining, and this is actually for soybean oil mostly applied, it remains highly reliable. It can deal with any kind of quality at the inlet. Unfortunately, there are the high oil losses and the soap stock splitting which is required. But with the nanotechnology, these negative effects can be somehow mitigated. So because we can use less chemicals, we have less losses, and we can have even more distillate produced in the deodorizer. And of course, we will have less sulfuric acid usage in the soap stock splitting, so also a lower effluent load. That's about it. Thank you for your attention.
Thank you, Bart. You did get several questions from the audience, but in an effort to try to keep things on time, I think we probably should move on to the next presentation.
Okay.
If you,
Sorry, it took some more time.
no, that's quite all right. If you can make it to the panel discussion, it would start at 10:05, so in about an hour from now. So,
Yeah. Okay.
all right. Our next speaker is Richard Ozer with Crown Iron Works, based in the Minneapolis area. Richard is a technical sales manager for specialty products at Crown Iron Works. He joined Crown back in 1997 and since then has been involved in applying Crown's existing solvent extractors in new applications. These new applications include things like soy protein concentrates for aquafeeds, desolventizing palm kernel, washing polymers, food grade citrus fiber, and other applications. And today he's going to talk a bit about white flake desolventization of oil seeds. So Richard, thank you very much, and I'll turn it over to you.
Thank you very much, and thank you all for taking the time out to listen. I'll try to make up some time if we can. The topic today will be about white flake desolventization, which is really about improving the value, increasing the value of your typical oil seeds. And when we talk, for the most part, the experiences with soy, but recent experience has been with other products such as canola or rapeseed and sunflower seeds. So whenever we talk about soy, please keep an open mind, and we'll be talking about other applications as well. But we're going to start with, pardon me, yeah, here you go. We're going to start with some definitions first. Is what is a white flake? So white flake is a hexane wet flake, and I'm going to expand that also to say solvent wet flake, because it can be alcohol or other solvents as well that are desolventized at low temperature to maintain product color and protein dispersibility. It's been applicable to soybeans as well as other oil seeds such as canola, rapeseed, and sunflower. PDI is protein dispersibility index, a test to indirectly measure the digestibility or viability of a protein. It's also an indirect measurement of the heat treatment of the product. SPC is soy protein concentrate, a highly concentrated soy protein, 65% and above protein level on a moisture-free basis. And it's most often processed with using white flakes with a PDI between 65 and 70 for food applications. Soy protein isolate is even more highly concentrated at 90% protein concentration, again, moisture free. And it's processed using soy flakes. There to improve yield, PDI is, let's say, 90 and above. Here you'll see a few pictures of white flakes. The one on the left is for making soy protein isolate. It's a 90 PDI. The color is a little bit better, although I don't know that you can see it in the photo here. It's a thinner flake because we're going to dissolve this in water. And then the 60 PDI white flake for making SPC, you're going to see that the solids are thicker and there are less fines present because that will be a water extraction, and fines, we don't like fines in extraction plants. The typical specifications will be really max PDI reduction between 5 and 7 points. If you bring in something with a field with from the field with a 90 PDI, we'll deliver it at 83, or at 95 PDI, we'll do it at, let's say, 88. We generally target less than 350 parts per million residual hexane in the product. Applications, where am I going to use this? And what we're going to say is that typically a white flake will have a sales value probably 30 to 50% higher than the typical high pro meals. So where are they used? The 90 PDI material, again, soy protein isolates, although there are other applications as well. The 60 to 70 PDI products, the big user is soy protein concentrate, but we also use this in bakery mixes where people have a requirement for gluten-free flour, donut mixes, the pastas. A very, very big use for white flakes, 60 to 70 PDI white flakes is texturized vegetable protein. What is that? That is a meat analog. That is a meat analog, and it's a substitute for meat. Basically, much better for the environment. It's a new product that's on the market, and quite frankly, again, it's what we do is we take the white flakes, we texturize it, we make it into a crumble that can be added to meat, or it can be served as a meat substitute by itself. Fully toasted, this is enzyme inactive at this point. It's used as a milk replacer, it's used as a filler in meat products and hard biscuits, and it's used as a flavor carrier. How do we make them? The work started in the 1940s and 50s when the USDA was looking for increased application of soybeans in the market and to make them digestible for ruminant cattle. They had to reduce the urease and the other anti-nutrients in the soybeans so they could sell the soy as a feed for cattle, piglets, and poultry. The work that was done by USDA showed that urease and most of the anti-nutrients became more sensitive to heat as the moisture content in the product increases. And so this work resulted in the development of the toasting process that we know today. In a desolventizer toaster, what do? We basically increase the moisture concentration so the proteins and the urease become more sensitive. The result of the work is really shown in this graph here, that basically tracks different temperatures, moisture concentrations over time, and then the denaturization in terms of a percent. Basically, when the moisture concentrations of your material are low, you'll see that, let's say 6% at 80 degrees C, the PDI remains almost constant. The drop is less than 5 points in 30 minutes and 6 or 7 points in an hour, and not very much different after an hour and a half. As the water content increases, you can see that after 1 hour at 15 to 20% water, after an hour, the PDI drop goes up a little bit. More so after 90 minutes, and after 2 hours, there's a pretty significant drop. When the product is dry at 8%, it's pretty stable for the first 30 minutes, but then it takes off at 120 degrees C. But at 115 degrees C, and more important, 20 to 30% water, and that's really down as low as 18% water, we see a reduction in PDI of 60 points in 30 minutes. So the graph shows that at 80 degrees C, the protein is relatively stable for extended periods, even with moistures up to 20%. But when temperatures exceed 110 degrees C, rapid protein denaturization occurs regardless of moisture content. But when the moisture content goes, like it should be 18% at 110 degrees C, we see that rapid denaturization or reduction of PDI occurs. And so this is where we make the 30 PDI for cattle or 20 PDI for poultry. And the rules are being, let's say 18 to 20% moisture, 110, 115 degrees C, and 20 to 30 minutes, you'll have a product, a high pro meal that will be suitable for feeding to cattle and poultry or other ruminants. So let's take this and now let's apply it to humans or to higher value type products like the calves milk replacer we talked about, or other products here, and the meat analogs. And we say that, how can we improve the value and then use the information we've gathered to improve the value of the product by making a higher PDI material? So we know that 10% water, the white flakes are resistant to denaturization for 30 minutes. We also know that when it's dry, in other words, without condensing sporage steam into the white flakes, it's possible to remove the majority of the solvent at atmospheric pressure without denaturing the protein. So as far back as 1967, a two-step method for desolventizing white flakes was developed. The first was to remove the bulk of the solvent at atmospheric pressure. Hexane's low boiling point of 69 degrees C protects the product at the low temperature range at atmosphere. And once the majority of the solvent has been removed, we fully desolventize the white flakes under vacuum and low temperature to prevent protein denaturization and also increase in color or decrease in color content. So it becomes possible to fully desolventize the soy and other oil seeds while minimizing the reduction in PDI. We have two different approaches depending upon the size of the plant and the application of the white flakes downstream. We can do it with what we call a downdraft desolventizer using indirect heat exchange at low temperatures. Desolventization takes 10 to 15 minutes, but from the chart before, we know there's no reduction in PDI. Conveying is mechanical, so the flake integrity is maintained. Or we have an alternate approach, the flash desolventizer, where heat exchanger is direct. In other words, superheated solvent comes in contact with the flake directly, and we desolventize the product as quickly as possible at temperatures from 150 to 100 degrees C, and then discharge to a lower temperature area right away. Material is conveyed pneumatically in superheated hexane at high velocities, so residence time is very short, 6 seconds, and you've gone from, let's say, 30% hexane to 2% hexane. The downside is that the turbulence and high velocity break flakes and you have higher horsepower involved. The upside is that your color is very, very good. In both cases, the DDD and flash desolventizer, the final stripping takes place under vacuum and at low temperature to minimize protein denaturization. The downdraft desolventizer is it's an indirect heater, and what we're doing is basically we're indirectly, in other words, we have a steam chest, and basically these red areas here are channels for steam. We're heating a plate. We're using introducing feed material here. We're using paddles to draw the material down the slope. Inside or on top of the heat transfer surface, it comes to the end of the slope here, And you'll see that the material falls off the end of the tray and it's gathered by the second tray underneath it. So the material is moving very straightforward on top of the trays in a snake-like pattern. And basically what happens is two things, is that we're turning the material over often. So we're always presenting hexane to the surface. So the evaporative, the boiling point of the hexane is protecting the material. The other thing that's extremely important is we have a plug flow or first in, first out situation here, so that material that enters, we can say with a surety that the residence time in the vessel is designed, let's say 12 to 15 minutes, but plus or minus no more than 30 seconds to a minute. So we have uniformly treated the white flakes. We have a feeder that will gently distribute the material over the width of the device. There's gentle turnover to keep the, like I said, the solvent wetted flakes in contact with the heat transfer surface without breaking the flakes. And if necessary, let's say when you're running at 50% of rate for some reason, you can turn the temperature down on and the pressure down on each tray to really control the heat input to the product. The next step, the next alternative is the flash desolventizer. And these are built for up to, currently built for up to 1,000 tons per day input of soybeans. Again, it's a pneumatic conveyor. Our feed point here is right here, just above this rotary valve. We're providing duct work that's going to provide the required residence time for the solids. The solids are removed from the system in a cyclone. There's a fan, a specially designed fan to work with solvent vapors. We recirculate, and the majority of the hexane or solvent will go back to through a heater where it's returned, and basically we start the process again. To keep the system in equilibrium, we have to vent any evaporated solvent away. So after the fan, there's a pressure control valve that vents the solvent and keeps the system in equilibrium. Direct heat transfer device, high turbulence to ensure good heat transfer and uniform product treatment. This is a first in, first out design also. Where the residence time, like I say, instead of minutes, 12 to 15 minutes, is 2 to, let's say, 4 or 5 or 6 seconds. And if you look at this device here, you'll see this is nothing but a bunch of turns. And this is an existing, pardon me, I'll be showing you in an existing installation in just a minute. There's a lot of horsepower associated with this elbow, these elbows and ducting arrangement that we have set up differently so we can provide the residence time without paying for all the horsepower. This is a flash desolventizer that was installed in Iowa, roughly 520 metric tons per day of white flakes. And this is a little one, basically a downdraft desolventizer for 100 tons per day of white flakes. The space taken up by this device here is perhaps 10 meters by 15 meters by 8 meters high. And you can see this is taking up almost a building. So the downdraft desolventizer packs a lot of heat transfer area and a lot of volume into a very, very small device. What's important to the vacuum stripper, that final step? So what are the essentials? We need to maintain product temperatures below the protein denaturization point, and even while adding stripping steam. So for soy proteins, the temperature that most of these proteins will denature at is about 80 degrees C. But we've been involved with some other proteins where we require temperatures as low as 57 degrees C. And basically, you're able to control the temperature that the solvent boils off at by controlling the vacuum. Simple as that. So lower boiling point is obtained by lower vacuum, and again, good product temperature control. So what else is important? We've got to provide residence time, because now in the first step, we're dealing with solvent that's on the surface of the product that's easily removed by evaporation. Now we need to provide time for the solvent to get out from the center of the particle to the surface where it can be carried away. So we provide several different driving forces to pull the solvent out. We've got to provide residence time. We also have to provide, we do operate under vacuum required to obtain stripping without condensation, because condensation results in bacteria growth. Condensation is water. We have a high protein feed material, and it's warm in areas and not necessarily hot. So we need to operate under vacuum. We also need to get to low ppms of hexane for storage and transport. And again, our target is the 350 ppm for traditional oil seeds. Another argument for vacuum, quite frankly, is you'll use less steam. We'll use stripping steam to carry to achieve the low ppms. And if we operate at under vacuum, we can, for an 800 ton per day plant, we can use 1,000 kilos per hour of steam. That same plant operating at atmospheric pressure will use almost 2.5 times more stripping steam than the operation under vacuum. Other things we have to look at, if you're operating with a vessel that's under vacuum, we've got to minimize in leakage of non-condensables, such as air, to minimize the load on your mineral oil system. We've got to provide cooling if the material is going to be stored, maybe not so much cooling if the product will be processed immediately after. And like I've said here, that the benefit of the operation under vacuum is the reduced sparge steam load. Now what we'll do is we'll look at the vacuum stripper by itself. Here, again, we basically the vacuum stripper is up here. And some customers like to go directly from the vacuum stripper, and they pneumatically convey the product away to provide the cooling on the way to storage. Other customers like a cooler directly underneath here. And so basically what we're looking for is we need individual trays to provide product temperature control or time, really for stripping. We're adding the sparge steam in the bottom tray of the vacuum stripper here. We're controlling levels on each tray to provide good contact between the stripping steam and the white flakes. We have devices in place to minimize the amount of in leakage or ambient air. And again, we point out that some customers like the cool immediately afterwards. This system is installed in Brazil, and the vacuum stripper is up top. You can see these coils here are half pipes designed to prevent condensation on the inside of the vessel. This can be, you can use steam coils, or alternatively, we can use electrical tracing. And this is the cooler portion of the system, where we a typical DC arrangement. This particular one was designed for 700 metric tons per day of white flakes. And we have designs on board for capacities as high as 1,200 tons per day of white flakes, be it canola, be it soy, or sun, depending upon customer requirements. I had mentioned that we have different ducting arrangements. This is the FDS, the flash desolventizer, mounted directly above the vacuum stripper with the cooler. This is a plant that's installed in Indonesia. A second plant is currently under construction, where a flash desolventizer has been installed with a piping arrangement to minimize the horsepower requirement. Again, these elbows are nothing but pressure drop. They provide residence time. They provide a lot of turbulence for product breakage, and with abrasive materials wear. In the case of palm kernel, which carries silica with it, you'd like to minimize wear. And you'd also like to minimize horsepower. So basically, different layout designs are available that, quite frankly, reduce the horsepower by as much as 40%. The plant that's currently under construction, I believe, is 1,200 tons per day of whole palm kernel seed. Sometimes we're making simply SPC, and where we are looking for a reduction, the majority of the product, we're looking for to reduce PDI to 60 to, let's say, 70%. We also want white flakes, large flakes, for downstream extraction that's being done. So in situations where we want to minimize the breakage of flakes, we'll use that DDD mounted above the vacuum stripper. The DDD will provide a nice reduction in utilities compared to the FDS. Quite frankly, sometimes for I think for 300 tons, the difference in horsepower for the DDD, connected horsepower for the DDD is, let's say, 5, which is, let's say, 3.5 kilowatts, and for the FDS is 250 kilowatts. The FDS has also been used, and there's two systems involved, 2 or 3, pardon me, systems that have been used in the world where product color is very, very important. Heat input to the product needs to be minimized to get the best product functionality. In situations like that, maximum time allowed for the majority of solvent removal is less than 30 seconds. And in those type of situations, the only type of heat device that heat transfer device or desolventizer that can be used is, let's say, a double flash line. This is installed in Europe right now, where the solvent is an alcohol, a hydrous ethanol. It's not hexane, it's not high strength ethanol, it's hydrous ethanol, maybe 35% water, where a good portion of the evaporation takes place in the first stage. The product is collected in a cyclone, passed to a second stage, where, let's say, the residence time in here would be 2-3 seconds, and plus the time in the cyclone. And in here, it's, let's say, 3 to 4 seconds, plus the time in the cyclone. Pardon me, where we're going from, let's say, 55% moisture and high and product that requires a lot of heat input because it's hydrous, before it discharges at roughly 1% moisture and enters a stripper, a vacuum stripper. We had talked about applications for the white flakes. And so the primary ones are soy protein concentrate. This is where we make the Impossible and the Impossible burgers and other meat analogs. And so soy protein concentrate can be used as a filler for processed meats like salami, frankfurters, kibasi, sausages, where basically the product will hold more water after it's been cooked. And so basically that would be one application. Another is the textured soy concentrates, where again we're making a meat analog, where it can be used as a replacement for schnitzel or beef or other different products. And these are a couple of applications where the product is a crumble as opposed to it's a crumble, and it's being added here as a powder. And in these particular applications, it's being extruded into that crumble and then formed again into a schnitzel, the crumbles here, or the chicken strips. This is a huge and a very, very high value, product, where we're taking the soy, I believe might be $450 a ton, a high pro, and we're converting that into a $600 to $700 a ton product for the white flakes. And when we start to get into these products here, they're $1,100 to, let's say, $1,500 per ton, or even more, for the finished product. Another application that's really growing is soy protein concentrate in aquaculture and feed. And so let's say when we're feeding salmon, carnivorous fish such as salmon, tuna, and other products that are other fish that are starting to be farmed, soy protein concentrate is a really good replacement for fish meal. And so soy protein concentrate is also important for the aquaculture as a high protein and less expensive. Typically, soy protein concentrate for aquaculture is made from a high pro soy meal, and the value of the SPC that's made for aquaculture or feed tracks the price of fish meal. It's generally, let's say, 30 to 40% less than fish meal. So if fish meal is costing $1,500 per ton, the soy protein concentrate will sell for $1,100. If the soy protein concentrate, if the fish meal sells for $1,100 or $1,200 a ton, then the SPC will sell for $700 or $800. The important thing to keep in mind is that it's possible to make pretty good money, pretty good margins when the SPC goes down to $700 a ton. SPC is also used to replace fish meal in calves and piglets' milk replacer. When I was introduced, we talked about specialty extraction, and this is white flakes are a very, very big portion, and SPC is a big portion of our product line. Crown does a lot of work working with other products. So what I'd like to talk about now is just for a little bit, what other products can we extract? And so using the same basic technologies of percolation or immersion extraction, it's possible to extract and dry a lot of other products that you might consider to be waste, as in the case of the fruit fibers. And you can have a valuable fibrous fiber add for addition to food. Other things like other insecticides like neem or perhaps pyrethrum, you can extract these products and sell them in a concentrated form downstream. So this is just a short list of other products that we've extracted at Crown. Whenever we work with new products, it's necessary to do test work. So we maintain a full pilot plant in Blaine, Minnesota, where we can test products on a 5 to 10 or 15 kilo basis, or we can do in larger scale equipment. We can test up to 6 tons a day in a percolation extractor. In our immersion extractor, which is right over here, we can test, let's say, 1 to 2 tons a day. We can produce quantities of material for testing, for product and market type of introduction work, and then also a confirmation of design. And with that, I very much appreciate your kind attention and any questions you might ask.
Thank you very much, Richard. We're going to have to also postpone the questions that you received to the Q&A session at the end during the panel discussion in an effort to stay on time here. Thank you very much.